So my name is Kautz. I lead the learning and perception research team at NVIDIA Research, and I'd like to tell you a bit about the work I've been doing recently on image synthesis and translation. In particular, we've been using generative adversarial networks for that particular task. So what do I mean by image translation? So in some way, you can think about it as the task of enabling machines to have human-like imagination abilities. And they don't mean like actual creativity, but being able to solve a task such as this. So given an input image, I would like the computer to take this input image, which was taken during the day, and map it to a nighttime image. So I want to learn some function, some mapping function F that turns this image, say, into a nighttime image, or maybe into a rainy day image. So translate it into a slightly different domain. So in this case, I've translated the daytime image into a rainy day image. This was actually generated using our method. So this is what I mean by image translation. Can a machine take an image and then sort of hallucinate what it would look like in a different domain, during the day or during the night or in the winter and so forth? Now, you might ask, why do we care about this particular task? Turns out there's a lot of image translation tasks that people actually care about. And that might be going from low resolution to high resolution, going from blurry to sharp, going from an image to painterly style image, going from low dynamic range to high dynamic range, taking synthetic data and make it look like real data, or going from one mode like thermal to a color image, going from a daytime to a nighttime image, going from a summer to a winter image, going from a noisy to a clean image, for instance. And for some of them, it's pretty clear why you would want to do this, right? From a blurry image to a sharp image, well, you want to remove the blur so you have a better image. You might wonder, why would I care about going from a daytime image to a nighttime image, or from a summer to a winter image? It turns out that, as you've heard in some of the previous talks, that machine learning requires a lot of labeled data, right, which is difficult to acquire or expensive to label. So if you can synthesize additional training data using an automated method, then that's beneficial. So if we only have training images that were captured in the summertime, if I convert them to wintertime, now I have effectively increased my training set, right, without having had to capture more data, which of course is beneficial. Now, the way we've been solving this particular task of image translation is in a learning-based fashion. So instead of just learning some arbitrary function f that does this translation, we learn it based on some training data set, right? So we have training images that will allow us to learn how to perform this particular mapping. And the method that we've been employing for this, or the underlying method that we've been employing for this are the so-called Generative Adversarial Networks, or also called GANs. Peter Abil, if you were at the keynote, mentioned them briefly. And they're really quite interesting. So what generative adversarial networks do is the following. They're usually structured to have a generator and a discriminator. And you start with some latent code Z. It's just a random vector, essentially. You feed this into this generator, and it's sort of the opposite of what usually a neural network does. It goes from this small latent vector and sort of expands it into an image. This is what the generator does. And then on the other side, we have a discriminator, which will tell us whether the generator actually generated an image that looks like our training set. So we don't say you have to generate images that look exactly like my training set, but we're asking it to generate images that look somewhat like the training set. So if I'm asking the generator to generate images of driving street scenes in the summer, I expect the discriminator to be able to distinguish whether I've actually generated a random noise image versus an actual image that looks realistic. The interesting thing is that at the beginning, of course, neither the generator nor the discriminator are trained. They're both neural networks. The weights are set to something random. So initially, the generator will actually just generate some kind of random noise pattern of some kind. And the discriminator won't actually know whether this image is real or not. But its task is to figure out over time what is a real image, what is a fake image, or not similar to the training domain. And then we ping pong, training the generator for a while, the discriminator, and so forth. And ultimately, you get to a stable state where the generator can actually generate realistic looking images, and the discriminator can't tell them apart anymore from your training set. in order to perform image translation, we use what's called conditional Gans, where we don't just have a random vector as the input of the generator, but rather either another image or a label map or what have you. So it's conditioned, the output of the generator is conditioned on something else. So in this example, it's conditioned on a nighttime image, and the task is to spit out a daytime image, for instance. And this is what you're going to look at today. There's various methods to do this, and they can be classified along two axes. That's what I'm doing today. I'm going to classify them along two axes. One of them is supervised versus unsupervised. Supervised methods is what's predominantly used nowadays in deep learning, where you have labeled data. So you have an input and the desired output, right, which is labeled data. So in this case, I might have images of edges showing shoes, and I might have the actual shoe that corresponds to those edges. So in that case, I have a paired input, right? There's the input and the desired output, which is yi in this case. Unsupervised in this particular context means that I don't have paired inputs. I still have training sets, so I still have, in this particular case, a training set of images that were acquired during the day, and I have a separate training set that was acquired during the night. They're not in one-to-one correspondence, which means I don't have, for the top image, I don't have the exact corresponding nighttime image, because that's basically impossible to acquire. And there's many cases, in particular for image translation, where this is impossible to get. You can't actually get a labeled training pair for this particular task. Because in order to get a labeled training pair, I would need to be at that particular position on the road, take this picture during the daytime, then wait until nighttime, take another picture from this same perspective, but also with the same cars not having moved, the leaves all being in the same place and so forth. So it's impossible to actually do this at large scale. So instead, in that case, you want to rely on unsupervised methods where you have similar training sets, so they're from a similar area, so they share a lot of commonalities, but one is captured during the day, one is captured during the night, but they're not paired. The other axis by which you can classify these methods is unimodal versus multimodal. So when I do an image translation, I might want to translate, in this case, just as an example, a dog to a cat image. And if I do a unimodal translation, I will only have one output image. However, in many cases, you can, of course, envision if I have a daytime image, well, there might be multiple nighttime images that make sense, right? One nighttime image might have moonlight, and the other one might not have moonlight. They're both nighttime images. They're just slightly different. So some methods allow for this, and the multimodal methods where the output of the translation can vary. There's sort of a style that you can change in the output. You're still doing the translation to the correct domain, but the domain might entail or might have different styles. And over the past few years, many techniques have been proposed along those lines that if you classify them, supervised, unsupervised, unimodal, multimodal, many methods have been proposed. And Peter Biel showed cycle GAN, which is where you go from horses to zebras, for instance. And they're all slightly different. And I'm going to talk about a few of them that we proposed recently. The first one I'd like to talk about is Pix-to-Pix HD. And this is a supervised method for image domain transfer. It is multimodal, so it allows multiple different outputs in your translation. And this was something we presented at CPR last year. So here, the task is fairly specific. We want to take a so-called label map, which is the first part that you see here, where each pixel is colored differently, and the color corresponds to a particular semantic meaning. For instance, the dark aubergine-like color is the street, the pink is the sidewalk, blue are cars, green are trees, gray is buildings, and so forth. So given such a map, can I learn what the corresponding real image would look like? So I want to synthesize an image where the cars are in the right place, the sidewalks in the right place, the tree are where I indicated I would like trees to be, and so forth. So how can we do this? How can you map from this semantic label map to an actual realistic-looking image? Well, it's very similar to the original Pix-to-Pix work, which also came from Berkeley, where it's essentially a conditional GAN, where you have your label map as input, you have a generator, you have a discriminator. In this particular case, the discriminator sees not only what the generator does, but also sees what the label map actually looked like. So the discriminator has sort of an opportunity to inspect the label map and decide whether the sidewalk is in the right place and the trees are in the right place and so forth. Again, generator and discriminator need to be trained. Initially, they don't know anything, but over time, when you ping pong them, you can actually learn both a generator and a discriminator that are good at their task. Our addition is that we made this multimodal, apart from also changing the training itself a little bit. But it's multimodal in that once we've trained the network, we know how to synthesize an image, so we can give it a label map and it synthesizes a real image. We look at all the instances of things like sidewalks and roads and cars, and then cluster all the features that are underneath a particular label and find sort of the dominant modes. And the dominant modes might correspond to sort of pavement versus cobblestone, or red car versus blue car versus black car, right? And once I found these, I can, when I synthesize an image, so when I use a generator, I can actually put this in and say, I would like the mode to be like cobblestone, or I would like it to be a blue car and not a red car. So this is quite neat. The way we trained this is, at the time, it was different than what most people did. Now this is sort of a common way of training GANs. Where we've used a coarse-to-fine generator, where we first train a smaller network. So the generator first outputs basically a lower resolution image, and also takes a lower resolution semantic map as input. And then we train this to the end. And then once that works well, we expand it and add sort of layers at the front and at the end to go to higher resolutions. That seems to stabilize training a lot, and it also means that you can synthesize larger images, which is quite nice. We use multi-scale discriminators, meaning the discriminator that has to tell whether an image is real or synthesized can look at multiple scales, and not just in the RGB space, but we also use this robust objective, which basically means it looks at the features that are being synthesized versus real features. So it's like a VGG loss for the discriminator, and it works on the discriminator's features. And that seems to help quite a bit as well. So let me show you some examples. So here, given the label map on the top right, we're synthesizing different results, and we just change the different modes. So you see we go through cobblestone, a different pavement, and we change the color of one of the cars as well. So it's all the same input label map, but the output, we change the style for each component that we're outputting. And overall, it does a fairly good job. So the images are mostly realistic. You can tell the car sometimes is not perfect. But overall, it's pretty decent. If you take sort of a quick look, you might not notice that it's actually a synthesized image. So next, I'd like to show you how we can change labels. So first, we change the labels from the trees to buildings, or the other way around. And then we change the sky also to trees. So you note the cars remain in the same place, the sidewalk remains in the same place, but then, the background changes from trees to buildings to trees and more trees. This is just a quick comparison to some previous work on in A and B, so that was previous work, and then at the bottom is ours, with the new discriminator loss and without it. And it works quite well. So that was our first task. We wanted to do this on images, and it worked quite nicely. Ultimately, though, what we wanted to do is actually perform this on a video. So we didn't want to just do images, but really videos, because it ultimately can lead to something interactive. So here, what we're given now is we have a video of label maps. So each frame is a new label map, but of course they're temporal. So this shows where the trees are, where the cars are, where the road is, and so forth. So now, of course, the first thing that we did is we just applied our method on each individual frame of this label video. And then you get something like this, which is, not great, right? So each individual frame looks just fine. But if you string them together into a video, it flickers a lot, which is not surprising because it doesn't know anything about the previous frame that it synthesized. There's no temporal coherence, because we didn't ask it to be temporally coherent. It's still decent, but it does flicker, which is, again, not surprising. So how do we fix this? Well, we took the learnings from the Pix-to-Pix HD and applied it to videos. So the training we changed a bit. So now it's a sequential generator where we feed in not just a single frame of a semantic map, but also some previous frames, so there's some history that a neural network can look at. We also feed it in the past images that we've synthesized, which is also helpful. In addition, we compute the flow between the past images that we've synthesized, so we know how things move over time. And then we can sort of project this forward and sort of predict what the next frame might look like given the previous frames. This is what is called the warped image here. And then, in addition, we synthesize a new image, which I will explain in a second, and then we combine this warped image with the synthesized image to get our final image out. The way we synthesize one frame for this video is very similar to the Pix-to-Pix HD case. We still use multi-scale discriminators, except now multiple scales means spatially as well as temporally. So we first discriminate at different spatial scales, but also temporal scales, meaning that we look at sort of frames that are further apart and frames that are closer together, temporally speaking. We also continue to do with a progressive training. Now it's spatial temporally progressive. That means we still start with a lower resolution generator that synthesizes an output frame at a lower resolution. And then over time we go to a larger resolution. In addition, we do this temporally. So first we synthesize images at some spatial distance away, at some temporal distance away, and then we make them closer and closer. So we also do this in a spatial temporally progressive way, just we do it spatially progressive. And then we ping pong between space and time when we synthesize it. So let's see what this looks like. This is the input, and this is the output. So now you can see it's temporally stable. You can still see some areas where it's not perfect, but overall it does look like a driving video, right? And all the networks I've ever seen is label maps and what an image might look like. Let me play it again. And all the network gets as input is this label map, and it manages to take this label map and actually turn this into a driving video, which I think is actually quite surprising that you can learn this at this quality level. Right. So this is in comparison to some other methods. Again, on the right is our previous method that we worked on a frame-by-frame basis. Lower left, some other state-of-the-art method, and on the bottom right is ours. And there's some different examples. And it even manages to do a reasonable job at synthesizing pedestrians. You do see sometimes that colors of cars change slightly over time. Right, I think this was the end of it. Right. So this was applied to driving videos. We can do something similar to human faces if you're training on edges to faces. So here we have the lower left, which is the input, which is an image of your human face, finding where the nose, eyes, mouth are, and then edges for the hair. And then we synthesize 3 different versions of this person. And we can do this because we clustered what people usually look like. So things that they never found is different skin tones and different hair colors. So we can create 3 different versions that have a slight different appearance. And then we played the same trick that Peter Bill showed in the Berkeley work. Here we train basically on skeletons of people dancing and real dancers. And then we can make it dance, just given some new dance. We synthesize this colored figure and then translate this colored figure into the actual person. So we track, given any dance video, we can track the person using skeletal tracking, synthesize this colored or render this colored person here, and then translate this colored person into this dancing person. And you do see some artifacts, but overall, it's pretty nifty. Right. So those methods were supervised. So you always had paired training input. Now I'm going to talk about some methods that are unsupervised, where you don't have paired training input. This is a bit older work. So instead of having matching pairs that I can use for supervised training, I only have data sets of different kinds, but of the same scene overall. So here, driving videos of the same area, some taking it during the day and some taken during the night. Now we want to synthesize, go from one of these domains to the other. And we're going to go both ways, actually. We're going to go from x1 to x2, as well as from x2 to x1. And it actually turns out that you want to do it both ways because it helps with training. So if you think about what I said before about conditional GANs, right? I could train it just like any other conditional GAN without thinking very much. So I have my generator. It takes in images of daytime. I have my discriminator, which will check whether the output image looks like a nighttime image. Or if I go the other way, I have a nighttime image as input, and the discriminator will check whether it looks like a daytime image as output. Now, the problem is that the discriminator doesn't actually know anything about what the input image looked like, and hence what the nighttime image should correspond to. So what will happen if I just train it without any other constraints is that, yes, the generator will actually learn to generate a nighttime image, except it won't be a nighttime image that corresponds to the image that I input, because there's nothing that makes it be the same, right? All I'm asking the generator is to generate a nighttime image. The discriminator needs to figure out whether it is a nighttime image or not. And they will both walk away happy, even if it doesn't actually correspond to your input image on which you want it to be conditioned on. So we need to make some additional assumptions, or it's not going to work. Right? So in this unsupervised image-to-image translation work, the assumption that we've made is what we call the shared latent space assumption. So again, I want to go from between these two domains. Then we assume that given, let's say we have a corresponding pair given, which doesn't really exist usually because we can't capture it, but if we had two images, then we make the assumption that I have an encoder, E1 and E2, that can encode from the first domain into this latent space and give me this vector Z, this latent code. And this latent code is constant, independent of whether it's a nighttime image or a daytime image. Right? So this is sort of the description of the scene, but without fixing daytime or nighttime. So just a description of this is taken there, and there's cars in that scene, and there's trees, and so forth. But I'm not telling you whether it's a nighttime or a daytime image, because from this latent space code Z, I can then use either generator 1 or generator 2 to actually synthesize an image for the domain that I want. So I can take my latent code Z and synthesize an image during the day and an image during the night. And I can, depending on which generator I use, it will give me one or the other, or I can generate both. So this is a bit more like an encoder-decoder architecture, right? Where I'm trying to take an image, I encode it, so very similar to many other works that are being done. Then I go into this latent space, and this latent space is sort of meaningful because it describes a scene without actually fixing whether it's a daytime or a nighttime image. Now, but as I said, we need to have, let me click through these. So now I can, if I want to translate an image, all I need to do is I'm going to encode my input image with the encoder 1, which goes into my latent space. Then I use my encoder G2 to output an image for the nighttime. Now, I need to constrain this somehow, right? That was my point, the point that I made earlier. I want to have some constraints so that actually the nighttime image actually corresponds to the daytime image, or any of these three images up there will be good translations because they are at nighttime. So what we do is the following. Yeah, both the encoder as well as the generator, they're all neural networks, right? So in order to have some constraints, we take the encoder E1 and E2 and actually share weights between them, even though they're actually meant to encode from one domain, from domain 1 to Z and from domain 2 to Z. We're going to share weights for some part of the network, not all of it, just the layers that are closer to the latent space. They share weights independent of the domain. And the same thing happens with the generator, where the generator shares weights going from the latent code to either domain, which means that if you take your latent code, sort of the early layers of your network will create sort of the basic structure of the scene. And then the later layers of the neural network for either generator, they will be different, and they will be the ones specializing either into daytime or specializing to nighttime, so depending on whether it's G1 or G2. And this additional coupling helps to make sure that the scene I generate is actually similar to the input image. So in this case, this is what it looks like. I have my daytime image on the left, the corresponding nighttime image on the right, and they actually correspond to each other. So the way I can go, so if I want to translate an image, I go from through the encoder 1 and decoder 2, and I translate from daytime to nighttime. If I want to go the other way, I just use encoder 2, go through decoder 1, or generator, I should say, and synthesize the daytime image. For training, I can do the following, which is the way we actually train this, is I can go back to myself, right? I can take my daytime image, I encode it, it ends up in this latent space, I decode it, and it should look like my input image because I'm going back to the original domain that I was already in, right? And that's sort of one way of training it. So what does this actually look like? So these are results. So on the left is input, on the right is always the output. So this is daytime to nighttime. And this is, again, these are not paired inputs, right? We've never seen pairs of images of daytime to nighttime. We've only seen videos of daytime, videos of nighttime, and they don't actually correspond pixel to pixel to each other. So what it's learned, the network, is that, well, the sky should be dark at night. Nobody ever told it, right? It's only seen images of daytimes and nighttimes, and it figured out that the sky should be dark, right? That should turn black. The road should still be lit, but not as much, only sort of near your car, because that's where your headlights shine light on. It's also learned that the colors of the cars are basically all dark, right? You can't really tell colors anymore. Anything sort of on the side of the road is usually also dark. So all the trees and so forth, they're also almost black. It's learned that taillights are illuminated, so it makes them bright, and sometimes it makes them red, which is what you see at night, right? It also learned, and some of these things are kind of funny, it also learned that usually, or not usually, sometimes there's light somewhere, right? So here, it thinks, well, these trees, there might be lights. So it puts lights into various places because it's learned that sometimes you see lights on the side of the street at night. So it puts light somewhere. But overall, it's quite sensible what it's actually learned. And again, it wasn't explicitly told to do these things, right? It figured out by just looking at daytime images and nighttime images that it should do these things, which is really quite amazing. Brief examples of turning a snowy road into a summer road. And again, we trained on two separate sets of winter images and summer images. And again, it's learned that in the summer, there's no snow, right? It removes all the snow and makes it just either grass or more shoulder. It learned that trees usually have leaves, right? So all the trees that don't have leaves, it puts leaves on them. And here's something that's actually really interesting to look at. Sorry, let me go back a little bit on this one. So if you look here, right, electricity post, looks a bit like a tree if you don't know what trees are. And it decides, well, it looks a bit like a tree. Let's put some leaves on them. So it turns these electricity posts into trees, and sometimes the wires as well. It puts some leaves on them, which is, it's not quite right, but it's not a totally silly thing to do either, because they do look a little bit like trees, and you could imagine that they have leaves, right? But overall, it managed to do very well on its own without actually having been explicitly told what's what. And also, if you look at things like the snow and the snow, it turns it into shoulder, so it learned that it should be removed. It's really doing quite well. And here's an example of sun terrain. So again, it learned the sky should be more gray if it's a rainy day. It learned that the road is probably more reflective because there's water on it, so it makes them look more reflective. It also learned that sometimes taillights look more illuminated because of the mist and the spray from the water. So some of them, they're glowing red, which is quite cool. So in this case, we actually didn't train it to be temporally coherent, but it does actually a pretty decent job, surprisingly. Right. So this was sunny terrain. So this was our first foray into unsupervised image-to-image translation. And this was unimodal, so you could only get a single version of your rainy time image, right? You couldn't do multiple versions. So then we continued working on it and came up with this sort of M-unit version, which is an unsupervised and multimodal image domain transfer. So it's very similar to the work that I just presented, except that in addition to having this shared latent space, which in this case here is called C, where you can map from your first domain into this latent space and then sort of back into the other domain, and vice versa, we have this additional style space where whenever we encode an image from one domain, we also try and figure out what the style code is. And style can mean different things depending on your domain. We actually don't prescribe what style means. It sort of figures it out on its own. For instance, it can mean, for nighttime, it might mean there's more light or less light. For summer, it might mean there are more or less leaves. For cats, it might be different breeds, right? It figures out the style on its own. Right, and the way we train is actually very similar, except that we have this style encoder where you can go to a style space, and you can use, and it's used when you actually synthesize an image. And this actually looks very similar to what we've previously done, except there's this sort of new thing down here where we encode the style, and then we have a style code in addition to the content code, and we use it to feed it into the generator, and the generator takes the style code, and when it synthesizes an image, it adheres to that particular style code. Right, so we can do things like, take an image of edges of shoes, and then translate into various types of shoes. So in this case, just given these edges, it does pink shoes, black shoes, beige shoes. The same for sneakers, and we can take the handbags, the edges of handbags, and it's learned that if you have a handbag with a pattern on it, it can have different colors, right? Or the patterns translate to different colors. It's really quite something. We applied it to similar scenarios before. So at the bottom here is summer to winter and winter to summer. And it's learned that if you go from summer to winter, there might be more or less snow. Or if you go from winter to summer, there might be more or less leaves on the trees. Here we go from a real scene to a rendered scene. So we train on real driving videos and synthesized driving videos in a game. And it learns that there's things like rain, snow, at dawn or dusk. And then here we go from a rendered image to a real image. And it learns that there's different types of cobblestone, I think, if I can see this right. Right, so we can do the same thing for translating images. Here's this Yosemite, which we trained on Yosemite images, where we go from summer to winter, and it learned that, yes, winter usually has snow, but it can be at different times of the day, for instance. Or if you go from winter to summer, the summer can also be different styles, so at night or during the day. And here we did a funny little one where we translate dogs to cats. So we capture just dog videos or dog pictures and cat pictures, and it learns that there's different breeds of cats, and we map sort of the pose of the dog to cats by translating. But we can translate to 4 different cats, right? And they all do the same thing that the dog does, because each of them runs this image translation. But we change the style code, so we have 4 different types of cats as a result. And here we just go through different, so through the style code. So you can see that if you map sort of from a big cat to a house cat, there's different breeds of house cats. And here we map from cats to dogs, and we move through that style code for different dogs. Right, and then you can, of course, do things like if you have different content and different style, you can apply this in a matrix. So you can have all different styles of shoes, different types of shoes and different styles, and apply them all to all. So you get this whole matrix, which is kind of neat. Right, so this was the multimodal unit. And then much more recently, my team did some work. I wasn't actually personally involved, but my team, in collaboration with other teams, worked on what we dubbed GAN. Is upcoming at CVPR, and you might have seen this in the news. It's again another version of mapping a label map, in this case to a landscape, but it's an interactive version, an interactive tool, and I'll run the video. So you can draw on the left. You can draw things like sky, clouds, water, and so forth, and then it'll synthesize an image that corresponds to your label drawing. So it's sort of like painting by numbers, really. And now we're changing it. There's water. We're drawing a little bit of rock. So it synthesizes this rock. Drawing a little rock. It's synthesizing a little small rock. You can draw a little mountain, and it does that. Again, it's multimodal, so I can change the style according to some other image. So you can, again, change it to river or gravel in this case, and it does more like a river. I'm going to draw more clouds, and then some grass, and a mountain. Switch through different styles, make it all cloudy. And then we draw a tree. And then the next thing is really surprising, actually. So we changed the style. So we changed, the grass in the front to snow. And then, because you changed the front to snow, then it sort of figured out the mountain in the background should probably also have snow. And it did this automatically. We didn't actually tell it explicitly. It just figured out if there's snow in the foreground, the mountain probably also has snow in the background. Then we draw a little pond, and it also learned that if there's a pond, there probably are reflections in it, and it actually learned to reflect the tree that was there. And it does that, again, it did this automatically. Nobody told it explicitly to do this. And here are just different examples of someone drawing and the synthesized images with it. So code's available for this. Right, so in conclusion, I've talked a lot about learning-based image translation, where you want to go from one image domain to another image domain. Based on some training data, it could be supervised or unsupervised. Of course, unsupervised is more difficult, but it's still quite powerful what you can do. And we've done this in a unimodal as well as in a multimodal fashion. And that concludes my talk. Thank you. I don't know if you're taking questions. Are we taking questions? Yeah, I think there's a mic. I don't know if it works in the hallway. Or if you shout loud enough, yeah. Go ahead.
For instance, if it's snowing, then playing with the amount of snow or something that would be as a trajectory for the level of snow or other related.
Yeah. So if I can rephrase your question, is sort of what influence do we have on the style that we're synthesizing if we do a style? So at the moment, the style itself is not disentangled. So you can still think, if I map from daytime to nighttime, there's different sort of axes of nighttime, right? There might be more or less light. It might be more or less snow on the ground, or whatever it is. And we don't disentangle these at all, right? So when we change the style, it might change all of these things together because we did not disentangle them. If that answers your question.
Hi, thank you for the talk. I wanted to know, you now showed a lot of examples for supervised learning and unsupervised learning.
Yep.
There is also semi-supervised learning, so having
Yes.
some paired data and a bunch of not paired data.
Yes.
Any new developments on this?
So in other unsupervised methods, all of them can do semi-supervised as well. So if you have some supervision, you can use it, and it clearly improves the results.
Hi, I guess my question here. Hi, I'd be curious to learn your intuition or motivation behind using GANs for all of these tasks. Can a very deep convolutional neural network not achieve these tasks, and why?
Right. So that's an excellent question. So it depends a bit on what the task exactly is, right? So a common example of using a GAN is for synthesizing like faces, right? Peter Biel showed an example where he showed really realistic faces. There is no good way of determining whether a face looks real or not, right? So there is no good loss function for you to sort of write that will tell you, is this face a good face or not? So the reason for using GANs is when it's difficult to write down a loss function, well, let's just learn the loss function, which is the discriminator, essentially. So in tasks where it's really hard to tell, like, is this a good nighttime image? I can't write down a loss function that will tell you, right? In that case, GANs are an appropriate tool. Now, there is some work that actually tries to not use GANs, but sort of uses clustering to get some latent codes, and then sort of trains them with a traditional neural network method, so deep learning based. And that works too. So there is some work in that space. Most people tend to prefer GANs. There's more work in that space, so we've achieved more so far. Not to say that maybe there are other methods that could be used instead, like VAEs or normalizing flows and so forth.
Okay, I have another question too. It's regarding interpretability. We know that CNNs are fairly hard to decipher, like the weights they learn is not very easy to decipher. What about GANs? Does that apply to GANs as well?
Yes, it applies to GANs as well, except for, of course, a GAN actually synthesizes something, right? So you have, it's a bit easier to see what happens in a sense, because the output is, if you synthesize an image, the output is an image. So you have some idea of whether it did the right thing or not, right? You can actually inspect it, the output at least.
Okay. Thank you very much.
Thank you.
Hey, I was just wondering if you could provide some detail on like how coupling the mapping function is different from like training the GAN sequentially using images from the two domains.
What do you mean? Sorry, I'm not sure I understood.
Like training the same GAN first with the images from the day and then the night, versus like coupling the weights, using the weight sharing you mentioned.
So the weight sharing is really necessary for there to be an additional constraint. If you don't do weight sharing, you just train them, nothing so what happens, there's an equivalent to mode collapse, right? Nothing prevents the generator from generating just a single nighttime image, and the discriminator will not be able to tell that something's wrong because you actually synthesized the nighttime image, right? There's nothing wrong. So you need to add some additional constraint, like the weight sharing, to ensure that this doesn't happen. Does this answer it?
Yeah, thank you.
Yeah, I have a probably a silly question. So, for autonomous driving, if you're driving on a night condition where it's very hard for camera to recognize or like segmentation, does it make sense to use GANs to translate night real images to daytime images and using that to help make decisions?
I would argue against it. No, the reason is because, as you saw in some of the examples, right, again, sort of hallucinated additional things because it thought, well, there might be something there, especially if you go from nighttime where there's a lot of things you don't see, right? It might hallucinate, well, there might be a tree over there, because it's a reasonable thing to assume, but it might just not correspond what's actually there.
Thank you. That's all the time we have.
Okay, thank you.